Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're trying our hand at tailoring. This is a matter of this is a classic problem where you loosen a belt that's tightly wrapped around the Earth and want to see how much extra space you give the Earth, with the belt not quite so tight. There's a classical version where the solution is awfully simple. And if it were just that, then I wouldn't consider it worth making my own video about. It's been done numerous times by other YouTubers, but there's also a harder version of this problem that I haven't seen anybody present a solution for. And that's what prompted me to actually make my own video about this. So, the original problem statement. Suppose that the Earth is a perfectly smooth ball, so no mountains, no valleys. You can argue whether or not you worry about oceans. And suppose it's perfectly spherical, with radius 4,000 miles. Suppose a belt was tied just tight enough to perfectly fit around the Earth. And it means around a full great circle of the Earth. Suppose the belt was loosened by 10 feet. How high would you be able to pull the belt above the surface of the Earth? Now, there are two ways of interpreting the question, how high can you pull the belt above the surface of the Earth? In the classical version, you bear in mind that gravity kind of pulls equally in all directions, and you're creating this belt with a low Earth orbit, if you will. Obviously, this is not drawn to scale, but just enough for you to see it. But to my mind, how high can you pull the belt above the surface of the Earth means you pull as hard as you can in one direction, so that while the belt is tangent to the Earth around most of it, it then takes off, and at this one point has some elevation. And intuitively, that should give you a higher height, right? Because you're pulling as hard as you can in one direction. And the classical version is a lot easier to solve, and is solvable with, I would even say, elementary school formulas. A harder version, the only way I can see of doing it by hand, only gets you an approximation, not an exact answer, but it's a really, 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 really close approximation. It requires Calculus 2, or Calc BC. So let's look at the classical version. We know that for a circle, C, the circumference, is 2 pi times r, the radius. Here, I'm going to say that r, the radius, is the radius of the circle that the belt makes. So, C equals 2 pi times 4,000 times 5,280. That's the number of feet in a mile. So we've converted our r to... So we say that if it were around the Earth tightly, it would be 2 pi times 4,000 times 5,280, plus an additional 10 feet. All right. So now r, the radius, equals c over 2 pi. So I say that r equals this c, this circumference, 2 pi times 4,000 times 5,280, divided by 2 pi, or plus 10, divided by 2 pi. I crunch the numbers, I get 4,000 times 5,280 plus 10 over 2 pi. But 4,000 times 5,280 is just the radius of the Earth itself. We're saying how high can you pull it above the Earth? So you get that it's radius of the Earth plus this additional 10 over 2 pi, which would be like 1.6 something feet. And a lot of people are surprised by that in a number of ways. First of all, you don't actually need to know the radius of the Earth in order to do this problem. Right? Any value you plugged in for this 4,000 times 5,280, those would just cancel out. Second of all, visually, a lot of people would imagine that loosening a belt that goes all the way around the Earth by 10 feet, they feel that would be negligible, that you'd hardly be able to slide a piece of paper under it. But they forget that these 1.6 feet are also negligible compared to the Earth itself, or radius of the Earth itself. So that's the solution to the classical version. Okay, now what about the harder version? And using a trick I've talked about a couple times, we invert the problem, sort of. That means swapping one of our knowns for an unknown. So we're saying we know the length and want to solve for the height. Here, I'm not going to assume that we know the height and solve for the length. I'm actually using an intermediate variable here. As I've drawn in this diagram here, the rope goes most of the way around the Earth, and then it goes tangent to the Earth at these 2 points. And you've got these 2 line segments that are tangent at these 2 points. You want to know the angle theta so you assume that you know the angle theta that is made between this vertical and this radius that forms that makes a tangent. Now you notice I've got these here and here. I've got these right angles there. That's because the tangent to a circle is always perpendicular to the radius at that point. Next thing I'll want to look at, how long is this line segment here, or this one here? Well, if this one here is r, then using trigonometry, this one would be r times tan theta, right? Opposite divided by adjacent. Now, if I measure theta in radians rather than degrees, the math just becomes simpler. If you want to measure it in degrees, okay, you'll just have to multiply by that factor of 180 over pi. But I'll break down my length into 3 parts. There's the round part of the length of the string here. That's going to be r times this wide reflex angle here. That's going to be 2 pi radians minus 2 theta. So r times 2 pi minus 2 theta. Plus, each of these lengths here is going to be r tan theta. So I get L equals r times 2 pi minus 2 theta plus 2r tan theta. Distributing, I get L equals 2 pi r plus 2r times tan theta minus theta. Get the 2r out here. Now, I know that L equals circumference of the Earth, 2 pi r, plus 10. Oh, one thing I should mention. Whereas in my solution to the classical version, I let r be the radius of the circle that the rope made. Now I'm letting r be the radius of the Earth itself. That's because this weird teardrop-ish shape that the rope makes, it's no longer a circle, so you can't really talk about a radius in quite the same way. So we said that L equals 2 pi r, circumference of the Earth. So it's 2 pi r plus 10, so you do the algebra. This term here, 2r tan theta minus theta, that has to equal 10, right? Because that's the excess. If L is 2 pi r, then it would fit snugly around the Earth. We have an extra 10 feet, so this 2r tan theta minus theta must equal 10. So we get tan theta minus theta equals 10 over 2r. Crunch the numbers here on what we said r was. Tan theta minus theta equals 10 over 2 times 4,000 times 5280, right? 4,000 miles times 5280 feet per mile. And one thing you could do is you could use a graphing utility like Desmos or TI-80 whatever, and get theta equals 0.00892 radians, if you want to solve it exactly. Now, what if you wanted a by-hand approximation, or at least an approximation that could be done with a scientific calculator rather than a big fancy graphing utility? All right. Well, to do that, we would have to rely on Taylor series. We have to use the result that tan theta is theta plus theta cubed over 3 plus something on the order of magnitude of theta to the 5th. And since we know already that theta is going to be pretty small, this theta to the 5th is going to be really, 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 really small. So I'll say that tan theta minus theta is approximately theta cubed over 3. Typically, you'll even approximate tan theta as approximately theta, but we need to go one step beyond. We need to get some sense of the magnitude of tan theta minus theta. So when we subtract out this theta, we need the next order term. So we'll say theta cubed over 3. This should be approximately, not equals. So theta cubed over 3 is approximately 10 over 2 times 4,000 times 5280. You get that theta is approximately 0.00892 radians. When you crunch this in, you actually get the same number to this many decimal places as you got before. Okay, now that we have theta, either by exact calculation or with a graph, or with this Taylor series approximation, how do we find the height? Well, once we know theta, let's look again. This diagonal here, we compare that to the radius of the Earth. That's going to be the hypotenuse over the adjacent. That gets you the secant of theta, or 1 over the cosine of theta. So we get h equals r secant theta minus r, right? Obviously, so the diagonals are secant theta, but we're talking about the height above the surface. So we use Taylor series approximation for secant theta. That's approximately 1 plus theta squared over 2. Plus, the next term would be order of magnitude of theta to the 4th. And again, since we know how tiny theta is, raising that number to the 4th is pretty insignificant. So we just do r secant theta minus r. We get h is approximately r theta squared over 2. We crunch in our number for r, right? 4,000 times 5280. We crunch in our number for theta, 0.00892, whatever. And we crunch numbers, we get it's approximately 840 feet. If we use exact trigonometry, we get 840.62 feet. And I later did further calculations. This 840 as opposed to 841 when rounding, that was because I rounded prematurely. If you use this theta approximation and didn't round in the middle of your steps, you'd actually get 840.62 again. So now this has the surprising result that by extending the belt only 10 extra feet, you can pull it over 800 feet in the air. Okay. I was surprised by that when I saw that. I said, wow, that seems really high, but yeah, apparently. So it does help to try to come up with an explicit approximate formula for the height h. So let's let x be the amount of excess rope. We said that theta cubed over 3 is approximately x over 2 pi r. Sorry, no, x over 2r. So we'll say that theta is approximately 3x over 2r to the 1/3 power. And h, we said, was approximately r theta squared over 2. Right? One of these comes from the tangent approximation, or the Taylor series of tangent. This one comes from Taylor series of secant. We crunch in r theta squared over 2, and what we get is 9r x squared over 32 all to the 1/3 power. And when you crunch that in, again, you can get that result. Another perhaps surprising thing, intuitively you might try to say, how high could you pull the rope per unit length that you add to it? It turns out it doesn't work that way. It's not a linear relationship. If you double the amount of rope, then the x squared, right, this 9r over 32 is just a constant. Right? And so you raise it to the 1/3 power, that's still just a constant. But then you have x to the 2/3 power. So if you double the amount of rope, your height will only multiply by 2 to the 2/3 power, or cube root of 4. But hopefully you found it interesting to note that you can get an explicit approximation that's still really, really close. As always, if you found this entertaining, liked the way I explain things, and want to arrange private lessons, feel free to click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.